Hi, my name is Kelly, and I'm going to tell you all about obtaining input data, some of the utilities available for manipulating data, and post-processing programs for converting and visualization of WRF model output data. I'll start with discussing mandatory input data, and then some sources for obtaining data, and finally I'll walk you through the steps of downloading input data. We very often get the question, what data are mandatory for running WRF? On the left, I have all the mandatory 3D or atmospheric data listed for both data on constant pressure levels and for data on native model levels. At the top right, I have mandatory 2D data. This includes surface and soil data. I want to mention that mandatory data is needed for all times you wish to run your forecast, so keep that in mind. The oval here at the bottom shows recommended fields. These are not mandatory, but they are highly recommended, especially for specific applications. For instance, if you're running long simulations more than about 5 days, it's necessary to have SST data. Most large-scale models, for example, GFS, come with SST data, but it's very coarse, so we always recommend including additional temporally higher resolution SST input. Sea ice is a good one to include for high latitude winter cases, though it's not required. WRF can be driven by analysis and reanalysis products or other global or regional model output. These are some of the more common global analyses. Here you can see the name of the product on the left, followed by the temporal and spatial resolution. All of these products provide global coverage, and then we list the temporal availability. You can see that some of these data sets are only more recently available, while some go back many years. For example, the NCAR-MMM reanalysis is available back to 1948, so you need to make sure the data set covers the date span you need. And finally, on the far right, there are links for obtaining the data. You can refer to the PDF format of this talk for easier access to the links. When you do download the data, always go for the highest resolution available for the area and dates you need. This should give better results in the end. This chart is just like the previous one, but these data sets only cover North America. Again, this chart setup is the same, but these data sources are geared toward climate applications, which are simulations spanning many, many years or decades. Climate data almost always comes in NetCDF format, so once you download it, you'll need to convert it to intermediate format to be run through the MetGrid program. I'll discuss this process a bit later. Many of the analysis and reanalysis products contain SST data. However, as I mentioned before, it's usually a very low resolution data set. And if you're running a long simulation, it's important that you also include SST data that has a higher temporal resolution. So these are some of the sources for obtaining those listed down here at the bottom. Okay, now I'll walk you through an example of downloading input data, starting from our WRF user's website, which is listed in the oval at the top left here. If you click on Download in the taskbar at the top of the website, you'll be given additional options. Click on Input Data for WRF. You'll then be taken to this page, which provides many of the same sources I listed on the previous few slides. For this example, we are going to choose the INCEP GFS, which has a spatial resolution of 0.25 degrees. You'll then be taken to the Research Data Archive website. These data are managed by the Computational and Information Systems Laboratory at NCAR. If you've never used RDA data, you'll first need to register. You can do this by clicking Register Now at the top. This is a quick process, and once you confirm your registration through email, you'll be allowed to log in. If you're already a registered member, you can simply log in. Once you get to the Data Informational page, click on the Data Access tab. Then you'll see a page like this, where you can click Web File Listing. If you happen to have access to the NCAR supercomputer, Cheyenne, you can instead click on the GLADE file system listing to obtain data directly. Once you click Web File Listing on the previous page, you can click Complete File List on this next page. You will then choose the year you need and then your dates of interest. At this stage, you'll choose the exact files you need. You need to make sure each time period is included by checking the box. If you have a lot of times you need, the RDA site provides the option to simply click the first and last time, and they will ask if you'd like to include all the times in between. So that's really nice. Once you have your times chosen, at the top you can choose your preferred method of downloading the files to your local system. Finally, this is the Nomad site, which is just an additional site where you can obtain many of the same types of data sets. For instance, NAM, GFS, Reanalysis 1, Reanalysis 2, etc. The link for this site is listed here in the bottom left corner. Okay, now I'm going to move into discussing some of the utilities we support, as well as several externally supported applications. I'll start by discussing applications for GRIB and intermediate formatted data, then how to design a model domain, some various NetCDF tools, utilities written specifically for using with WRF, a program called ImageMagick for converting graphical files, and then some special WRF output variables, the OBSGRID program for nudging purposes, and finally, the MET Plus verification package. Most input data will come in GRIB format, either GRIB1 or GRIB2. If you're interested in more information about these two types of GRIB files, you can follow the links listed here under Documents. If you'd like to do some decoding or reading specifics of the GRIB data, there are a few different options. For instance, WGRIB and WGRIB2 for GRIB1 and 2 files allow you to look at the headers in the data file, which is the plain English of all the information stored in them. Along with the WPS package file, we provide G1 print and G2 print executables, which again correspond to GRIB1 and GRIB2. These are found in the util directory inside of WPS. These programs give nearly the same information as WGRIB, but not quite as detailed, but they're probably sufficient for what you need. For GRIB file formatting purposes, there are a couple of programs you can use. The GRIB to CTL program is available from NCEP and creates CTL and IDX files so that you can plot the GRIB files with grads. This can be useful if you want to ensure your GRIB data look reasonable. And there is an NCL program called NCL Convert to NC, which converts GRIB formatted files to NetCDF format. This allows you to take a quick look with NCView, which I'll discuss a bit later. When you run the ungrib executable as part of the WPS program, it converts GRIB formatted files to intermediate format. This is a binary format designed specifically for the purpose of using with the METGRIB program, which is also part of WPS. Occasionally, input data will come in a form other than GRIB format. For example, mini climate datasets are in NetCDF format. In order to use these data to run WRF, you'll first need to convert the data to intermediate format so that you can run the METGRID program to horizontally interpolate the input data onto your simulation domain. If you look in Chapter 3 of the User's Guide, which is linked at the top here, you'll see a section that describes the process for doing this, and this code shown here is just an example. If you're using NetCDF input data, we do have a Fortran script you can use to convert the data to intermediate format. If you follow this link shown in the circle, you'll be able to download that script. The script was provided to us from an outside source who used it for their particular application, so keep that in mind when using it. You will need to make several modifications for your specific case, but it can serve as a nice template. If you're interested in reading intermediate formatted files, there are a couple of programs that are useful for that. Shown on the left is an NCL program that opens the intermediate file, reads the header information, reads the slab information, and continues to loop until it reaches the end of the file and will provide the printed out information. The RD intermediate executable is found in the WPS/util directory, and it gives a text description of the code, which can be really nice for a quick look at the details. If you're interested in plotting intermediate files, you can use this NCL program called Plot Format, which is also found in the WPS/util directory. If you give it the intermediate file name, it will loop through and plot all the data found in the file. Again, this can be useful for verifying that the data makes sense. It can sometimes take a while to loop through though, so keep that in mind and you may have to be a little bit patient. For a better resolution plot of intermediate files, you can use the int to NC executable, which converts the intermediate file to netcdf format, and then use the NCL program plot format in C to plot it. Again, this will loop through and plot all of the data found in the intermediate file, and this could take a bit of time as well. If you're having a little bit of trouble designing your domain, we have this NCL script called Design Grids available that may be helpful. If you know some basic information about where you want the domain, such as the resolution, map projection, latitude, longitude, you can give the program these values and then run the program. And it will provide suggested name list options. You can start there and then play around with it to get it just right. You can obtain that script by following this link at the bottom. Now I'm going to tell you about some utilities you can use for netcdf data files. netcdf operators, also called NCO, are command line programs that take netcdf input, perform some sort of operation or function, and then provide output in various formats such as text, binary, netcdf, etc. These operators are free, and you can obtain them by following the link at the bottom of the slide. There are several different commands, and I won't show you all of them, but I'd like to discuss a few examples that we found to be particularly helpful. ncdiff is a useful command you can use to show the difference between two netcdf files, and then you can use something like the ncview utility to plot the differences if you'd like. And again, I'll talk about ncview in a few slides. NCR-cat allows you to write particular variables or times to a new file that includes only the data you want to pull out. For instance, here's an example where we are requested to pull out only the variable rain in C, or non-convective rain, for hours 0 through 231, and then we write that data to a new file called raininc.nc. You can also use NCR-cat to concatenate or combine netcdf files. Here we combine the contents of file 1 and file 2 into a combined file called combine.nc. NC rename allows you to rename different things within a netcdf file, such as variable names or attributes. This example shows that we are renaming land use to land, and the missing value attribute is renamed to fill value. There's also an NCO command called NCKS, where the KS here stands for kitchen sink, meaning this command does several different things. For example, you can extract a specific variable. Here we are pulling the rainnc variable out of the WRF Out history file and putting it into its own file called rainnc.nc. You can also split files. If we had a single WRF Out file that included 12 hours worth of output data, but we wanted to only look at a single time, we could split a file like this, asking for time 1-to-1 from the WRF Out file, and then put it into a separate file called wrfout1.nc. And of course, these output file names can be anything you like as long as they have the .nc at the end. This is just a list of some of the other available NCO operators. I won't go into details, but refer to the PDF version of this presentation on the web if you'd like specifics. You can also get additional details from the NCO website. NCView is something many of you have probably used before, especially if you are participating in this tutorial. It's a free tool you can obtain from the link at the bottom, and is essentially a visual browser for netcdf formatted files. It allows you to do many different things with all the variables found within a netcdf file, such as look at time series, vertical cross sections, and if your model simulation crashed, you can also use it to detect where things may have started to go wrong. Shown here on the left, I have a time frame at the top with some funky looking pixels, and then by the next time, it turned all white and the model stopped. This lets me know that something is wrong at the top of my domain. This tool works with any of the WRF files that are in netcdf format, so the geo, em, and met.em files from WPS, and the WRF input, WRF out, and WRF boundary files that are part of WRF. Within CView, you can also include boundary overlays, like is shown here for the United States. This option works with any gridded NetCDF files, so that would be the WRF input and WRF out files. However, to use this, each output time must be in a single output file. It won't work if you have multiple output times in each file. NC Browse is just another quick snapshot viewing tool, similar to NC View, but just with a different view. If you're interested in trying it, you can go to the link at the top. The NC Dump utility can be extremely useful for WRF output files. It reads a NetCDF dataset and prints information from that dataset. You can choose to print out all of the data, but for a more reader-friendly printout, I suggest using the -H like we have here, which just prints the header information. If you're only interested in a particular variable, you could use this -V option to print out the variable you want. You can also look at the time information for a WRF output file or WRF boundary file, for example. If you use the -V times command, it will provide the header information, but includes each timestamp at the bottom of the printout, like is shown here. Moving away from NetCDF, these are all the utilities that were written specifically for WRF files. The read WRF NC utility can read WRF NetCDF files and then outputs various types of data. IOWRF can extract a particular area of your domain if you wanted to focus on only a small part, and it has the capability of thinning or destaggering the data. WRF Interp can interpolate WRF output to several different level types, such as pressure, height above ground level, etc. It's also capable of performing underground extrapolation. P-interp is specific for interpreting data from sigma levels to pressure levels. V-interp allows you to add vertical levels in your WRF output after you've run your simulation. And diffwrf can do several different things, but I find the comparison of different output files to be the most useful. This is the only one that comes with the WRF code, and you can find it in the external/io_netcdf directory. All the others, you can find additional information and downloading information from the links listed here in the circle. I do want to advise you, though, that most of these utilities are pretty old and have not been updated for quite some time, so it may take a bit of finagling to get them working properly for your application. ImageMagick is free software that allows you to display, compare, manipulate, and convert images. It essentially converts to any format from any format. For example, if you have ImageMagick installed, you can simply use convert in the command line to change the format of a PDF file to a PNG file or to a BMP file. It has several other options available too, such as cropping out all the white space or setting the background to white. You can create a canvas based on white background and merge the layers. There are two different ways to use this software. You can choose to use the point and click method or do everything in the command line. It's up to you, whichever one you prefer. You can create movies by creating individual frames for each image. One of the best things about the software is that it maintains high resolution, which is something you'll want for publication purposes. However, if you happen to be working with the specific .ncgm files, which are the NCAR computer graphics metafiles, that is available as output from some of the NCL scripts, you cannot use this program. It won't work with those, but it does for almost everything else. If you're interested in downloading it, you can get it from this link in the bottom right corner. The WRF model outputs state variables, which are defined in the registry file. These are used in the model's prognostic equations. Some of these variables are perturbation fields, and therefore the following definitions for reconstructing meteorological variables are necessary. For example, to get the total geopotential, you need to combine perturbation geopotential with the base state geopotential. There's more information about each of these variables found in the registry.em_common file within WRF. Okay, now I'm going to talk about the OpsGrid program. OpsGrid improves first guess gridded analysis by incorporating additional observational data. Take a look at this figure, and let's suppose we are looking at lines of constant temperature from the first guess gridded data. But if we had an observation that said that there is a point out here that should be matched with the green temperature, We could use ObsGrid to modify the input to look something more like this. It's likely the ObsGrid program will not be something you need. Traditionally, first guess analysis came from low resolution global analysis and forecast grids. These days, higher resolution regional scale analyses are more readily available. It can be useful, however, if, for instance, for whatever reason, you must use some sort of older, very coarse data, or if you have access to some very high resolution point data. For example, if you conducted a field campaign and gathered a great deal of very high resolution data, you'll want to incorporate that into your simulations. To use ObsGrid, you first will download the source code. You then must configure and compile the code, and the code must be compiled serially. There's no parallel option for this utility, but that's okay because it runs very fast. You then will need to prepare your observation files. Each user is responsible for preparing their own data. You then make modifications to your name list and then link in your input data or your MET-EM files from WPS. After that, you just run the program. If you're interested in this option, check out Chapter 7 of the WRF User's Guide. The entire chapter is dedicated to this program, and there is a lot of information in there. When you run ObsGrid, there will be several types of output files. You likely will only need to use one type, but it depends on your intent. The MET-OA files are final analysis files at both surface and pressure levels. These files include the observations, so they are very similar to reanalysis data. The WRF FDDA files contain surface analyses and all observations within 250 kilometers of each grid point. You would use these files as input to WRF if you were doing surface analysis nudging. The OBS domain files include all the observations available. These are used during WRF if you're planning on using observational nudging. When you run ObsGrid, you'll have an OBS domain file available for each time period, and they'll be in chronological order in format of OBS domain 101, OBS domain 103, etc., each ending with an odd number. To use these files for observational nudging, you'll need to make sure they are all concatenated to a single file called OBS domain 101. This is the file name that the WRF program will look for. You can use the run cat obs file script that is included with the program to do the concatenating. If you have any questions about these, again, I'll refer you to Chapter 7 of the WRF User's Guide. For more information about nudging in general, refer to the presentation on FDDA. Moving away from ObsGrid, I want to briefly discuss MET+. This is a verification framework that spans a wide range of temporal and spatial scales, from storm scale to global. It's intended to be extensible through additional capability developed by the community. On the left, I have listed the three core components of the framework. MET, which stands for Model Evaluation Tools, and includes all the basic statistical tools such as root mean square error, bias, etc. It also includes some more advanced special methods like wavelets and objects, as well as confidence intervals. MET Viewer and MET Express are the associated database and display systems. And there's a suite of Python wrappers to provide low-level automation and examples, also sometimes called use cases. For all documentation, how to download, and for support information, see this link provided here in the circle. That concludes the utilities section. Now let's talk about some post-processing and visualization options. This chart displays the post-processing packages that are maintained and supported at NCAR. The package is listed on the left, followed by documentation and information, such as what it is and where to obtain support. Not all of the packages are supported by our particular WRF support and development group. You'll notice that only NCL, ARW Post, and RIP are supported by our group. Before getting started with a post processor, you'll want to weigh all the options and determine which tool is best for you. There are several things you may need to consider, such as can it handle staggered grids, or how is data handled below the ground? You'll want to know if it's easy to use. You don't want to spend all of your time trying to use a tool that's very difficult. The cost of the package may be a consideration. Is it free software, or will you or your institution need to pay for it? How well is the tool supported? This can be very important because if you get stuck somewhere, you want to know whether you'll be able to receive useful help along the way. Can it read your data? Also very important. There is no use in downloading and learning about a tool if it can't even manage your data. Along those lines, can it handle big data sets? These are data sets that are large, probably high resolution over a larger area or many months or years of data, such as climate output. And which functions does it include? And if they aren't available, how difficult will it be to add new diagnostics? Here is a chart that shows the graphical tools across the top and data types along the side. Darker blue indicates the tool is capable of handling that particular data type very well. Light blue means that it can handle the data type, but maybe not quite as easily as some of the others. If the space is black, it means it is not at all capable of handling it. So you can see here that NCL is the only one that can read and plot NetCDF without a converter. The rest all have the converter listed in the first row. NCL is also the only one that handles all these data types really well, including big data. RIP, GRADS, and UPP can all handle big data, but just not quite as easily as NCL. And Vapor and IDV are not even capable of handling big data sets. This chart is similar, again showing the graphical tools across the top, but along the side are processing capabilities. Vapor and IDV are the only ones that do any sort of 3D visualization. NCL has some diagnostics, not a lot, but it's very easy to add new ones. RIP has a lot of diagnostics already available, and it's easy to add more, but maybe not quite as easy as with NCL. Vapor and IDV both have limited available diagnostics, and it's not easy to add more. Vapor and IDV are also not capable of extrapolating below the ground. So you may be asking, why would I even want to use Vapor or IDV? Well, I'll refer you to the material for each of these tools, but they make beautiful images and movies. They are great for wowing your audience, which may be exactly what you need to do. As I mentioned, most of the post-processing tools require a converter, so you may be wondering why this is necessary. The reason is that WRF output is on a staggered grid with the U and V components on the sides of each grid cell and all other variables in the center, or otherwise known as mass points. Post processors are not capable of reading this staggered data. They can only see the mass points, so the converter will co-locate all the U and V data to the mass points. The converter is also necessary for translating certain variables that need reconstruction, as I previously showed, such as geopotential height or temperature. That our team support are NCL, ARW Post, and RIP. For specifics on NCL, please see the presentation specifically devoted to NCL, which includes a lot of useful information on that tool. That leaves us with ARW Post and RIP, so we'll start with ARW Post. ARW Post is actually the converter, not the post processor. It reads in the WRF output, does its converting, and then outputs in GRADS readable formatted files. If you want to actually display the data, you will need to use GRADS to do so. But you don't need GRADS for compiling ARW Post. You can compile it separately. If you have any questions specific to GRADS, use the link provided here. For downloading information, please follow the link in the blue circle. And if you're interested in trying an online tutorial with step-by-step instructions, follow the link in the green circle. Recall that all of our presentations are available via PDF format where the links will be clickable. These are just some example plots from ARW Post. You can do contoured lines overlaying another variable, such as is shown in the top left, showing lines of sea level pressure on top of temperature fills. You can do something that is grid cell specific, like this vegetation fraction plot that gives each grid cell its appropriate value. It's capable of doing cumulative precipitation over a period of time, and it can do skew Ts. One of the cool things about the ARW Post skew Ts is that there is a built-in overlay option where you can plot two different skew T results on top of each other for comparison. If you're wondering why the plots all have this weird, what I call windshield wiper look to them, it's because it plots on map projections instead of an XY grid. These are some more examples of ARW post available functions. It's capable of doing cross sections. For example, if the bottom left here shows a horizontal plane, I can specify where I want a cross section across that domain. And the top left is the resulting cross section showing relative humidity here. It also has a zooming capability, which can be useful for viewing things more closely. These are all the available diagnostics built in with the ARW Post tool. For the sake of time, I won't read them all, but feel free to pause the presentation to get a thorough look. And these are all the available scripts included with ARW Post. These allow you to plot a color bar, change colors, and there are 79 different color options available. SKU-GS is how you would create a SKU-T plot. Rain-GS is what you would use for cumulative rainfall, and Cross-Z-GS is how you would create a cross-section plot. Okay, so now let's learn a bit about the RIP program. RIP stands for Read, Interpolate, Plot, and is a post-processing tool that generates graphical plots. To use RIP, you will also need the NCAR graphics libraries that you can obtain from the link provided here. There's documentation included in the downloaded file of RIP. You'll find it in the doc directory, but you can also see it online in the link here. I highly recommend paying attention to the documentation. There is a lot of very useful information included, and it can help you to find the needed diagnostics. One of the advantages of RIP is that it has a lot of diagnostics, but a disadvantage is that it's written in Fortran 77, which means it's easy to work with but can be difficult to change. You can obtain downloading information from the link provided in the blue circle, and just like with ARW Post, if you're interested in trying an online tutorial, follow the link in the green circle. These are some example RIP plots. Like with ARW Post, you can plot something like land use category that is grid cell specific. And it also includes the SKU-T capability, but without the overlay function. However, you can overlay several variables, such as is shown here in this plot on the right. We have a column of potential vorticity, contours of potential temperature, and then circulation vectors showing wind flow. There is also a really nice zooming capability included with RIP, where you can see some fine detail. It also includes cyclone tracking for those doing any sort of tropical cyclone research or forecasting. There's also a backward trajectory option. If you're interested in knowing where individual air parcels are originating, you could use this option to track them back in time. This is the flow for RIP. You start with your input data, which are the WRF output files. RIP-DP is the post-processor that does the necessary converting. It then outputs single files with one time frame and variable per file. You then run the RIP program with the specifics of the plots you wish to create, and you get some sort of output plot like this. For plotting specifics, use the RIP namelist file. There are many options available, not limited to those shown here. You can specify the processing times, plot title information or keys, the text quality on a plot. You can specify the variables and plot type, whether you want to do a trajectory, etc. You can also specify the format type for output, such as X11, where it just pops up on the screen, or something more permanent like PostScript or PDF. There is a full explanation for the nameless variables available in the RIP documentation, so take advantage of that. That concludes this presentation. Hopefully it was helpful.